lecture we continue the discussion on part subcontracting. As mentioned in the previous lecture, if we have a final solution like the one that you see here on the picture, there are 5 intercell moves, and if we are going to use part subcontracting as a way to minimize intercell moves, the first part that we can try and subcontract is part number 6. So, we try to modify the Bochter's formulation in such a way that we include part subcontracting into the formulation and we can try and solve it, rather than solve it without part subcontracting, and from the optimum solution or solution using any algorithm we try and identify which are the parts to be subcontracted. So, the Bochter's formulation has an objective function of minimizing the intercell moves x I k equal to 1 if machine I goes to group k, and y j k equal to 1 if part j goes to group k. The original Bochter's formulation will have sigma x I k equal to 1, which means each machine is assigned to one group, and sigma y j k is equal to 1, where each part is assigned to one group. So, now with part subcontracting being included, then all the parts need not be assigned to cells, while some parts are subcontracted. So, this can be written as y j k less than or equal to 1, which indicates that it could be assigned. If it is 1, then it goes into a group; if it is not 1, then it does not go into the group, it takes 0 and it is subcontracted. So, one way to do it is to write like this, or another way to do it is to say plus some zj is equal to 1. We have already used the notation z in an earlier lecture when we linearize this absolute value term. So, now if we do this, we have to use a different notation other than z to linearize, because we have used z here, and this z should not be confused with the other z that can happen when you linearize. Or we could even say S j equal to 1 if part j is subcontracted, representing S for subcontracting. Again x I j, x I k, y j k are binary. Now, we should look at some other possibilities that can happen. Now, because of this subcontracting, can we get into a situation where all parts are subcontracted in the solution? We have to ensure that that does not happen. For example, can we have a situation where all 8 parts are subcontracted, because this allows every part to be either put into the cell or to be subcontracted. We have not explicitly added a cost of subcontracting into the objective function. If we did that, then it will not take all of them towards subcontracting. So, now we have to check whether such a possibility exists. Suppose all the 8 parts go to subcontracting, then no part goes into the cell, and the objective function value here, because this a I j will be 1. For every a I j that is equal to 1, there will be some x I k that is 1, because each machine is allocated to a cell. So, this will throw out as many intercell moves as the number of 1s in the matrix, if all parts are subcontracted. So, ordinarily it will not allow all parts to be subcontracted, because this solution with 5 intercell moves is a better solution than saying all parts are subcontracted, and therefore, we will have that many intercell moves as the number of 1s. Because if all parts are subcontracted, all these are 0, but all these xik's will have to take a value 1 somewhere, and these aij's take value 1 at the relevant places. So, this will throw up a whole lot of intercell moves. So, in a way it is good that we have the formulation this way, and this should be enough. Sometimes we might like to restrict the number of parts that are subcontracted. So, we could simply add another constraint, which is sigma Sj is less than or equal to some capital P or whatever, to say that not more than 3 or 4 parts can be subcontracted. So, that will also ensure that too many parts do not go to subcontract. Again, this is a kind of an optional constraint, all these are enough to take care. Now, in the slide what I have done is, I have said that now when you give this condition, this is written from the constraint sigma yjk less than or equal to 1. Now, that is rewritten as plus Sj equal to 1. So, if we want to look at that constraint, we could try to either minimize the number of parts that are subcontracted or try to maximize the number of parts that go into the cell. So, the corresponding objective is written as maximize yjk. So, now this looks as a 2 objective problem. 2 objective problems are also not very easy to solve. So, it is okay to consider one of them as a constraint. So, when we take this as a constraint, the maximize sigma yjk as a constraint, yjk greater than or equal to some number, which is the same as minimizing the parts that are subcontracted and saying that not more than p parts will be subcontracted. So, this formulation is the same as that shown in the slide. So, as I again said, this is only an optional kind of a constraint. Even without this, the problem does not lend itself to a trivial solution. Sometimes change of something from an equation to an inequality can tweak the entire solution. That does not happen in this case. It does not say that all parts can go to subcontract. It is still economical from an intercell move point of view to have a reasonably large number of parts made in the cell and some of them being subcontracted. So, this is how part subcontracting happens, and this is how Bockter's formulation is modified. Similar modifications can be made in the p median formulation also, but we are not going to describe such modifications here. So, this is a constraint which says that a maximum of only one part can be subcontracted. So, either it can be written here as S1 plus S2 plus S3 plus S4 plus S5 plus S6 plus S7 plus S8 less than or equal to 1. The other way to write is y11 plus y12 plus y21 plus y22 etc. is greater than or less than or equal to 7. So, we would like to have actually greater than or equal to 7 will ensure that less than or equal to 7 will ensure that some parts are actually we want to maximize that. So, we should say there as greater than or equal to 7. So, the 8th part will go to subcontract and it will do. So, the optimum solution is given with part number 11, 31, 41, 22, 52, 62 equal to 1 and with z equal to 11, 7282 equal to 1 with that. We will now see that 6 is missing. So, 6 is subcontracted, part number 6 is subcontracted in this. So, having seen some of these ways to minimize intercell moves, we look at one more aspect to cellular manufacturing, which we are going to introduce here as remainder cells. Now, what are remainder cells and why are we talking about remainder cells? Now, when we looked at the cell formation that we have seen starting from production flow analysis, we now take data from an existing plant as to how the parts are manufactured, and up to now when in the production flow analysis or rank order clustering algorithm or the basic Bochner and P median formulations, we have assigned every machine to one group and every part to one group. Sometimes we have assigned more than one machine also to more than one a machine can figure in more than one group with multiple copies assigned to each. Now, this we can call as some kind of complete cell formation or normally called cell formation. Now, let us also look at what happens when variety increases in a cell. Now, what is variety? If we look at an incidence matrix like this, let us say these are 8 distinct parts that are produced in the factory, not in the cell, but in the factory. There are 2 cells in this solution. Now, if we introduce a 9th part, and if the 9th part, which is represented as column number 9, is say identical to column number 1, if it is identical to column number 1, including the column number 9 into the cell formation would automatically put column number 9 or part number 9 along with 1, 4 and 5, because it is identical. So, it will automatically go to the group 1, 3 and 4, except that additional capacity may be required in the group 1, 3 and 4, additional capacity for machines may be required. But if column number 9 is very different from 1, 2, 1, 4, 5, 2, 3, 7 and 8, let us say, then automatically column number 9 brings a certain variety into the system. So, variety is represented by the columns not being identical, columns being very different. So, when variety comes into the picture, already let us say this has 3 intercell moves in this solution. This does not show part number 6, this is a solution at the end of part subcontracting. But if we go back to a more familiar one, which is this, which has 5 intercell moves, and if I am bringing in a part number 9, now there are going to be more intercell moves coming out of part number 9. So, as variety comes in, as products change over a period of time, which results in more and more newer parts coming into the system, and each part being represented by a column, as products change, product variety changes, part variety changes, and this will result in more intercell moves. So, one solution is machine duplication, another solution is revisit and recreate cells, the third is to allow intercell moves. Now, once we start allowing intercell moves, we lose control. The primary reason for implementing cellular manufacturing is lost when we start allowing too much of intercell moves. So, what we do here is, for example, in this, if we take this as an illustrative solution, even without an additional part number 9 with the existing system, now we have one machine group with 1, 3 and 4, the other machine group with 2, 5 and 6, and there are 5 moves here. If we allow machine duplication, then the solution will be 1, 3, 4 and 6, 2, 5 and 6, and there are 2 moves which are here. Now this is going to be a little costly because this is an extra machine that I have to bring in. Now suppose I say that I have 1, 3 and 4 here, 2 and 5 here and 6 here, 6 here. Then I am going to have 6 is machine number 6, 6 is machine number 6. So I will have 3 visits from 1, 4 and 5, 3 visits from 1, 3 and 4, I have 4 visits from 2, 3, 7, 8, and I will have 2 visits between these two. In a way this solution is the same as this solution if I leave this portion. So instead of buying an extra 6 and putting it here, I am just pulling this 6 out and doing this. Now one way of looking at it is, now I have 3 plus 4, 7 plus 2, 9 intercell moves. The other way to say that if I am not counting these, I have only 2 intercell moves and I have not added a machine. Now I call this as a reminder cell or some kind of a service cell, where there are only 2 cells, parts can move from the cells to the service cell and go back. These are not counted as intercell moves, whereas moves only from these are counted as intercell moves. Now such an idea is called a service cell or a reminder cell. Now this is one way of representing it, and this becomes significant when variety increases. The same idea is expressed in the literature by saying that certain portion of the manufacturing system is grouped into cells and certain portion remains as a job shop or as one large service cell. So this is something like saying 30 to 40% of the machines will act as a job shop, while the rest of the machines will act as or will be grouped into cells. Now there are 2 ways of looking at the picture that I had drawn here. One is to say that if I create a reminder cell, my intercell moves reduce, but my moves into the reminder cell increases. So whether it is 2 moves or 9 moves or 11 moves, nine moves, 2 plus 2 plus 7, 9 moves. 7 moves were here, 2 moves were there. So whether it is 2 moves of yellow or 2 plus 7, 9 moves. So if we do not count the moves into the intercell to the reminder cell, then we have only 2 moves, but we lose so much of ownership and control. The only difference is the service cell or the reminder cell will look at each of these cells equally with equal importance, and since it does not have any part ownership, it will not treat any part as something coming from outside. For example, if I do this, if this is my reminder cell, in terms of machines, now in terms of parts 1, 4, 5, 6, 2, 3, 7, 8. Remainder cell does not own any part, parts are assigned only to the GT cells or the normal manufacturing cells. Because this does not own any part, it treats both these equally. It does not treat a part visiting here as an unwanted burden on the cell, whereas if there is an intercell move here, with part 6 going to machine 2, P6 going to M2, M2 is here. Now this cell will treat this P6 as something that does not belong to my cell, but this part is coming for machining, and particularly if this cell is going to be viewed as a profit making entity, and because this part is owned by this cell, whatever revenue or profit generated here, let us assume is not going to be added to this, or even that fraction is not going to be added, then this intercell move will be treated as an unwanted commitment of this cell to something else, even though in principle we should not be thinking so, that the organization in total is benefiting by it. But remainder cell does not have any part allocated to it, therefore it does not treat any of these as intercell moves or as something which is not its own that it is performing. At the same time, move is a move, so there can be delays and so on. So we will lose some control, but we have the advantage of not duplicating the machine. Machines are kept as a common facility. So that is the idea of the remainder cell, but in just to complete this, so one is cell formation where all machines are put to cells, one is a remainder cell formation, the third we call as incremental cell formation or product based cell formation. So here the cells are formed based on products themselves. So a complete product is made within a cell, whereas here we talk of machines and parts, here we talk of parts belonging to a product and machines. So here the variety is slightly higher, here the volume is slightly higher, so that we can create cells to make 1 or 2 parts. Here we have both variety and volume, mid volume, mid variety here. So these also are treated in terms of various classifications of the plants, where the literature has said that this is a slightly large variety manufacturing, where 30 to 40% go into a job shop. This is typically part machine cell formation, this is product machine cell formation. So if we really want to classify cellular manufacturing further into 3 types, one is the normal machine component cell formation, where the products are slightly larger in terms of size, involve specific common assemblies, parts are made into cells, parts go to the various assemblies. So finally for a particular product we may require parts coming from different cells, and the product is assembled and produced. This is applicable to the same scenario, but there is a large variety, therefore we are unable to create independent cells which will make a family of parts. Therefore we have a common facility where some of them will go into a common facility, you may call it a job shop, call it a remainder cell and so on. This is a case where the products are little smaller in size, there is sufficient volume, the cell is created, and everything from this cell will go to an assembly which is very close to or even within the very close to the cell or in the same area as the cell is, and the complete product will come out by pulling out from this cell. So this classification also is there in the literature. So with this introduction we will now see the remainder cell, after which we will see incremental or product based cells. So if we go back to the remainder cell, Once again we can modify the Bakhter's formulation for the remainder cell. So, Bakhter's formulation will be like this: minimize intracell moves the earlier version every machine has to be assigned to a cell. Now, the machine can either be assigned to a cell or can be assigned to a remainder cell. Just like in the part subcontracting, either the part can be made inside the cells or can be made outside the cell. So, in a similar manner we will say xi k equal to 1 is now written as plus some r k equal to 1 if or r I equal to 1 if machine I goes to the remainder cell. All right. R I equal to 1. So, next thing we have to ensure is that all the machines do not go into the remainder cell, because we are not going to add the intracell moves for the remainder cell. Again going back to the example, there is this, this and this, 6 was here, all these moves are not going to be added, only these moves are going to be added. So, we should not have a situation where all the machines go to the remainder cell. So, that is taken care by ensuring that there is a size restriction on the remainders. So, sigma r I is less than or equal to some r. I do not want more than 2 machines in the remainder cell, I do not want more than 4 machines in the remainder cell. So, there is a size restriction on the remainder cell. Now, every parts are not assigned to the remainder cell, parts are assigned either here or here. So, this is fine, yjk is equal to 1. Now, when machine number 6 is assigned as a remainder cell, going back to the matrix, if machine number 6 is assigned as a remainder cell, let us see what happens here. Now, machine number 6 requires 3 plus 4 7 parts. There are 7 parts that are there for machine number 6. Therefore, there are 7 places where Aij is going to be 1. Now, the corresponding parts are going to be assigned to cells, this is going to be 0. Therefore, this is going to overestimate it, or it is still going to add those 7 inside. So, we should now then do like we did earlier. So, we will do minus 4 R 1 minus 3 R 3 minus 4 R 4 minus 4 R 2 minus 5 R 5 minus 7 R 6. Why do we do this? If machine number 6 goes to the remainder cell, then 7 moves are absorbed by the remainder cell. They are not intracell moves, but they are 7 moves that are absorbed by the remainder cell. So, this will be overestimating it by giving us a value of 9 or whatever. Those 7 will be taken. So, that has to be subtracted. Similarly, if 5 goes into the remainder cell, then another 5 moves are going to be absorbed by the remainder cell. So, that has to be subtracted. So, this is one full term So, this is minus 4R1 minus 3R3 minus 4R4 minus 4R2 minus 5R5 minus 7R6, which is shown here as minus Aij xip plus 1 is your xr, subject to the condition xik plus xip plus 1 is equal to 1. This is the same as xik plus ri equal to 1. Ri is when it goes to the remainder cell, that xik plus xip plus 1 is equal to 1. So, a machine either goes to a GT cell or goes to a remainder cell. Yjk is equal to 1 is enough. We do not need to say even less than or equal to 1, less than or equal to 1 implies it could go for part subcontracting. So, we will restrict Yjk equal to 1, so that all parts are assigned to the remaining cells. So, when we do this, we could have a solution that has machines 4 and 6 going into the remainder cell with 2 intercell moves. The final solution will be 1 4 5 6 come here, 2 3 part families are intact, but we realize that 4 and 6 go into the remainder cell with 2 intercell moves, when the remainder cell has a capacity of 2. Let us just check that. If we had 5 and 6 go into the remainder cell, plus we put a restriction that each cell size should be less than or equal to 2 and 2 machines go to the remainder cell. So, 4 and 6 go to the remainder cell with 2 and 5 coming in. So, this problem is solved with 2 types of restrictions. This is equal to 2. So, 2 machines go into the remainder cell, plus we have also put another restriction that cell size, we said that in Bochter's term. So, xik summation summed over I should be less than or equal to 2 for every cell. So, this gave us the solution with 4 and 5 or with 4 and 6 going into the remainder cell with 2 intercell moves. Now, let us proceed to another aspect of cell formation, which is incremental cell formation or product based cell formation. Sometimes this is also called pilot cell formation and so on. Same terms are used interchangeably in the literature by different authors. Sometimes it is called pilot cell formation. Now, this happens in 2 different scenarios in manufacturing. One is, let us say we start implementing cellular manufacturing, and let us say we have carried out a production flow analysis. Production flow analysis, let us say, gives us 5 machine cells. First and foremost is, it is also it is not easy to instantly move from a conventional process based layout to a cell layout, because once the cells are formed, the machines have to be relocated. This would take time. At the same time, production should not suffer. We cannot, for example, stop production for 3 days or 4 days, do a complete relayout and start. That is not a profitable proposition for an organization. So, many times what organizations would do is, either on every holiday they will move machines to other places, and over a period of 4 months or 5 months, cells will slowly get formed, and the system will move to a cellular manufacturing system. So, let us assume in such a case we have made one cell and then we have to make the other cells, but once that first cell is made, that cell is tested, how is this cell performing, what are the other issues, so on. So, it works with only one cell. So, in such a situation you could call it as a pilot cell formation or first cell formation. The other would be, before going through a production flow analysis and finding out machine cells and part families, the organization picks up one product which does not involve too much of assembly and so on, or a product that is most profitable, either way, and create a cell for that product. So, in such a case also it becomes a pilot cell formation or product based cell formation. Take a product, find out what are the parts that are there, what are the operations that are required, and create a cell that will make this product. Sometimes the product is chosen more out of convenience for production, sometimes the most profitable product is also chosen. The other times what can happen is, there is an existing cell or there are existing cells, and due to volume and variety the cell capacity is already realized and there are just too much of intercell moves happening. So, now there is a need to redo this cell, and when we redo this cell there will be some interesting changes that will happen. This cell would be expected to produce at a slightly faster output than what it is currently doing. Therefore, newer machines will be brought in. Therefore, again the problem will be one of making one particular cell that caters to the requirements of either one product or very few products. So, we now bring all of these into the classification called incremental or product based or pilot cell, under the assumption that the volume is large and for a particular product we are going to create a cell. So, we can use the term called product based cell formation. Now, with this product based cell formation, we will now look at some aspects of this product based cell formation. So, we are again going to capture it in terms of an incidence matrix to begin with a very slight difference. The matrix remains the same, but the way this matrix is to be read is slightly different. Now, we are going to assume that there are these 6 operations that are going to be performed. The columns now represent operations on the product, and this cell is going to make that one product. Now, we can use the word product and part interchangeably. So, these 6 columns represent 6 operations that have to be carried out to make a part or a product, and this cell is going to make only that part or product. There is enough volume to do that. If we take the first, there are 6 candidate machines that are available. If you take the first operation, it can be done in either 1 or 3 or 4 or 6, unlike the earlier incidence matrix where it has to visit all the 4 machines. Now, we make an assumption that this operation can be carried out by 1 or 3 or 4 or 6. It is not an AND, it is a OR. So, the simplest problem is, in order to carry out all these 6 operations, what is the minimum number of machines that I require to create a cell? Note that part j does not visit all the machines where Aij is equal to 1. It is enough that part j visits one of the machines where Aij is 1 in that column. So, what is the minimum number of machines that are required so that a cell can be formed and this product can be made? So, we have a simple formulation where xi equal to 1 if machine I is chosen. So, in order to make the first product, I should have x1 plus x3 plus x4 plus x6 greater than or equal to 1. To make the second operation, I need x2 plus x4 plus x5 greater than or equal to 1. To carry out the third operation, x2 plus x4 plus x5 greater than or equal to 1. To carry out the fourth operation, x1 plus x3 plus x4 plus x5 plus x6 fifth operation 2, 3 and 6 and the last operation 1, 2, 3, 5, 6 obviously we want to minimize the number of machines that we choose. So, minimize sigma xj. So, there will be as many variables as the number of candidate machines, there will be as many constraints as the number of operations. The objective function is a straightforward objective function of minimizing sigma xj. All right hand side values are 1 and so on. So, this can be solved as a binary IP once again. So, for this particular example, this can be chosen. The optimum solution is x3 equal to x5 equal to 1. So, for this solution x3 equal to x5 equal to 1 and with 2 machines we will be able to do. So, x3 will do operations 1, 4, 5 and 6. So, x3 can do 1, 4, 5 and 6. x5 can do 2, 3, 4 and 6. So, x5 can do 2, 3, 4 and 6, can do. So, now it is up to us to say that we could choose this will do 1, 4, 5, 6, this can do 2, 3, this can do 1, 5, 6, this can do 2, 3, 4, we can choose anything from this solution. Ordinarily we would choose a solution with 1, 5, 6, 2, 3, 4 versus a solution 1, 4, 5, 6 and 2, 3. Ordinarily we would do that. It would also depend on the processing times and so on, but if we want to have better control or if we make an assumption that all the processing times are equal, then this would have a processing time of 3, this would have a processing time of 3, whereas this would have 4 and 2. So, the cycle time will be 3 here, cycle time will be 4 here. So, we would choose this instead of this. But all those we cannot do with the data that we have because we have not given the processing times. At the same time, simple thumb rule that you balance by giving equal number of operations will work. So, we need to look at few other aspects on to this problem. One is we should also at some point clearly say that which operation goes to which machine, because the processing times may be different. So, we need to bring in processing times into this picture. So, we need to bring processing times into this picture, which we have not done. Somewhere we also need to bring cycle time into the picture. For example, for the sake of illustration, if all the processing times are 1, then this configuration would give us 3 and 3 with a cycle time of 3, this configuration would give us 4 and 2 with a cycle time of 4. Now, suppose we want a cycle time of 2, then we should look at, instead of x3 and x5, maybe we will look at x1, x3 and x5. Maybe we will look at x1, x3 and x5, where x1 can do 1 and 6, x3 can do 4 and 5, and x5 can do 2 and 3. Obviously, we won't be able to get a cycle time of 2 by choosing this. So, a required cycle time may at the end of the day increase the number of machines in the cell. But we also have to keep something in mind, which is this: as a mathematical problem, we can simply add a constraint, assuming that we have processing times, which we have not done here, we will see that later, but we could add a cycle time constraint and take it. But we also have to understand that this cell, when made, has a realistic life of about 2 years, 3 years, 4 years, so on, whereas the required cycle time can vary every day depending on the daily demand of the product. So, one has to keep the cycle time within a realistic number, which can take care of peak demand or lean demand, because if we do it for very tight situation, then we create a cell with more machines, and on days when we do not require too much of that, there will be underutilization. So, there is always this trade off between cycle time and underutilization, cell size and underutilization and so on. So, we will be required to look at processing times, cycle times. We might also want to look at cost. Sometimes these 6 machines could be existing machines. Sometimes we would like to create a cell with completely new and bought out machines. Now, when we do that, the solution may change if instead of minimizing xj, we minimize cj xj. For example, machine 3 may be a very costly machine, and 3 may be substituted with some other machine here. So, cost also has to be looked at. And last but not the least, unidirectional flow has to be looked at. If we assume that to make this part or product, we need to follow the operation sequence 1, 2, 3, 4, 5, 6, then this does not give us unidirectional flow, because if we have M3 and M5, so M3 does 1, it comes here, then for 2, 3, 4 it goes here, for 5, 6 it comes back. So, this is not unidirectional flow. Similarly, this also is not unidirectional flow. So, unidirectional flow may give us a different configuration. Unidirectional flow can simply give us M4 and M3, with M4 doing operations 1, 2, 3, 4 and M3 doing 5, 6, or M4 doing 1, 2, 3 and M3 doing 4, 5, 6. So, we will have to look at all of these when we start creating product based cells. So, let us look at the next one, which is considering a cycle time restriction. So, this is our incidence matrix, which has cycle times. So, when we do a cycle time restriction, the formulation changes. So, the formulation will become xj equal to 1 if machine j is chosen, and y or xi equal to 1 if machine I is chosen, and y ij equal to 1 if operation j goes to machine I, goes to machine I. So, we have more variables that come in, and if we have a cycle time restriction, then we have to try and restrict the cycle time on each of these chosen machines and so on. So, we will look at this formulation and subsequent formulations involving processing time, cycle time, cost and unidirectional flow in the subsequent lectures.